Okay, let's get started. So, not much today, but let me okay. So here, again, reminder, quiz 4 and 5 online, right? So quiz 4 should be due in like 7 hours. So, okay. So today we'll be going over sort of not much more, but just how derivative and integrals, affect the power series. So recall from before, right? If you have a power series, and x to the n is power series with r greater than 0. So r is the radius of convergence, right? So radius of convergence. Then for any, for any number between it, right, our series, the power series sum n equals 0 to infinity, and x to the n converges uniformly on negative r1 to r1, right, to a continuous function. And we have that inside that the interval, right, the interval 0 to r, right, we can we have ddx of this, right, is we could bring it inside, right? So that's a statement. So in negative r, right, inside our interval of convergence, we could bring this in, right? So this, let me be clear, this is n equals 1 to infinity an times n x to the n minus 1. So again, really quickly, it's n equals 1 because yeah, so we are sort of missing the constant term. So for example,
哦，你
like
说完，我突然想起来，
你是不是没有了？
对，
用完了，这么大箱，我们之前在哪里买的
Amazon，我就看见 Amazon 没有了。
I could hear you, so maybe try muting yourself. Okay, so if we just had a polynomial, right? If an x to the n, if I take derivative, you see we lose this term, right? Term when taking derivative, right? So you see, we should start at 1, right? Because the 1 sort of represents like this term, right? This term doesn't get killed, but the first term does. So that's why we start at 1. Okay, and similarly, right? Integral sum an x to the n dx is this, right? Integral. And this is again inside our interval of convergence. And this is n equals 0 to infinity. Right? So this starts at 0 because when you integrate, no terms vanish, right? I mean, integral of constant is like, integral of like 2 is 2x, right? It's only when you take derivative, the constant term goes away. Okay, but so this is great and all, but the question is, are the series nice? So in other words, what I mean is our original series had radius of convergence r, right? That's why I put negative r to r. So the question is, does derivative and integrating sort of make it worse? Does derivative integrating, the series change the radius of convergence, right? So like basically I'm asking, does this thing also have radius of convergence R? And does this thing also have radius of convergence R? Should we plus the dot? Okay, so there's a theorem, so I'm not gonna, go over it, but it says that if sum n equals 0 to
对了吧？
infinity an x to the n has radius of
还是那什么
convergence R, then the power series, the one given by, the derivative n x to the n minus 1 and sum an over n plus 1, right? These also have radius, also has radius of convergence R. So this is nice, right? Because, I mean, it'll be really bad if yeah, you could bring the derivative inside, but the thing you get ends up like not converging on that radius, right? So okay, so this is pretty much the main theorem of the section, but there's also something called Abel theorem. Abel's theorem. So on your homework, there's something called Abel sums. So it's called that's if you want to look it up, it's called summation by parts, pretty much. So if you remember the integral, right? Integral has like integration by parts. So on your homework, the Abel thing is just instead of integrating by parts, you're sort of doing integration by parts with the summation sign. So okay. So anyway, let f of x be sum an x to the n. N equals 1 to infinity. Be power series with positive, positive finite radius of convergence. Finite radius of convergence. So in other words, R is not 0, R is not infinity, right? Of convergence R. So right now we have that, on the open interval, negative R to R, right? So here, so where is it? Right here, right? We have for any R1, right? So the question is, what about at the boundary point? What about at the point R and negative R? Do we get a continuous function? And it says if series converges at x equals R, then f is continuous at R. Right, so this is at the boundary points, and if series converges at x equals negative R, then f is continuous at R, right? At negative R, sorry. And that's about it. There's not much on this section, so let's move on. I think we could probably do all the questions in the book. So let's go 26.2. Okay. So first off, this is something, this is a math 2b question, but observe that n x to the n is equal to that function for absolute value of x less than 1. So we're going to use this, theorem we have, right? So want to show infinity is x over 1 minus x squared. Should I? Yeah, okay. So what we're going to notice is we know the power series for 1 over 1 minus x, right? So recall, so this is just geometric series, right? With a being 1 and your r being, x. Remember you get a over 1 minus r, right? So, okay. So we know this. So what is the derivative now? if you calculate the derivative, you will get 1 over 1 minus x squared. Agree? Quotient rule. But we want x times that, right? So let's multiply by x. So we get x times 1 over 1 minus x prime is x over 1 minus x squared, right? And then we use the theorem, right? We know the power series for 1 over 1 minus x. It's given by, so this thing is given by x times sum n equals 0 to infinity x to the n prime, right? So again, let me make this clear. This is x times d dx of this thing, right? That's what the prime means. Okay, so now we're going to use that theorem, right? Or not yet, but you know, basically we can differentiate term by term, right? So this part, we're going to use this thing, right? d dx, I could bring it inside provided I'm in my radius of convergence, right?
Oh shit!
So here, what is the radius here? The radius here is 1, right? It's negative 1 to 1, right? So in this interval, I get that this is, right? So it's only true in that interval, right? Because, you know, you can only move it because that's when your convergence is uniform. Okay, so this is just x. Now be careful. This is n equals 1 to infinity and x to the n minus 1. So again, it's n equals 1 because you lose your constant term, right? And if I multiply the x in, I get this, right? Agree? And that is what we have. And we're done, right? That's what we need to show. Okay, so that concludes the first part. And I mean, here, I mean, this thing, again, it's, you know, geometric series, you know, whatever you like, right? Ratio test. but really, you can see that the radius is 1, right? Because in this case, if you look at this, if you try plugging in x equals 1 on the left, you're dividing by 0, right? So the farthest you could go is 1. Okay, so let's move on. So I'll do B, and then I'll let you all do C for practice. So B, evaluate this sum, right? So now this is cool, right? This is getting a bit cool, you know, interesting, because they want us to evaluate this thing, right? But this is what? This is just this thing, right? It's just this thing with x equals a half, right? So again, if f of x is, then f of a half is certainly just this, right? And we showed that inside the interval negative 1 to 1, right? My function here, f of x, you know, in negative 1 to 1, I mean, from part A, it was x over 1 minus x squared, right? And certainly a half is in the interval negative 1 to 1. So sum n equals 1 to infinity, n over 2 to the n is just, I plug in a half. A half over 1 minus a half squared. What is this? 1/4. So it's 2, right? So you see, like here, we sort of represented a function as a power series. Okay, any questions so far? Okay, so you might wonder, you know, like, I mean, it's not really a surprise because it's in Math 2B, but can other functions, if I could write this one as a power series, can I write all the other functions I know as power series? So some classic examples, let me just write classic examples is e to the x is given by this, x to the k over k factorial. And you have cosine of x is given by, and then sine of x is given by, so cosine is sort of like the even terms, sine is sort of like the odd terms. So hopefully this looks familiar because there's something similar on your homework, right? Sort of show like the derivative of one is the other, right? I mean, if you think about it, in this case, derivative of cosine is kind of like sine, right? With a negative sign, and derivative of sine is cosine. So I think the series he gave on the homework is not exactly cosine and sine, it's the hyperbolic ones. So it's like, I think it's like hyperbolic cosine and like hyperbolic sine or something. Okay, so let's continue. So, right, so these are just classic examples. We're not gonna prove that. So square. Yeah, okay, so let's do 26.3. Let's see how this works again, right? So I need to know what, sum n squared is now. So want to derive explicit formula. What is this, 26.3? For sum n squared x to the n. Okay, so from previous problem, what did we have? We had sum n x to the n is what? It was this, right? Okay. So how can I go from, let's start off with this summation. How can I get an n squared? Any ideas? It's not that hard. I need to go from an n to an n squared. What operation do you know that that will bring an n down from the x, right? So here there's, you take derivative, right? And again in negative 1 1, because here I'm using the fact that this was the derivative, sort of like the derivative of this one, right? It was the derivative of like this. And the theorem that I just stated, right? Right here, this question, it says that these have the same radius of convergence, right? So when I take derivative, the radius of convergence doesn't change. So if the original had radius of convergence 1, so the derivative also has it. And here I get n equals 1 to infinity. So why is it n equals 1 here? Why did I not move up 1? Like, kind of like how I went from n equals 0 to n equals 1 last time. So the reason I went from n equals 0 to n equals 1 last time was because there was a constant term, right? And derivative of constant term is 0. So I'm sort of missing the first term. Here, there's no constant term, right? If you plug in n equals 1 to the, what's the power of x? The power of x is 1, right? There's no x to the 0 here. So you see I'm not losing anything. So the sum still starts at 1. Okay, So we're almost there. We have x to the n minus 1, and the problem wants x to the n, right? So, whoa. So what we should do is multiply by x, right? So I know x times sum is this thing, which is what we want. Now, from previous problem, on, negative 1, 1, this is just, the inside was just this, right? And then, from here, it should be simple, right? It's quotient rule. So please tell me if I'm doing quotient rule wrong, because I always make algebra mistakes. So I get 1 times squared plus. So it's plus because I chain rule the 1 minus x. Okay, so clearly I could get rid of 1 minus x on top and bottom to get plus 2x over cubed, and this is x times, what is this, 1 plus x over, yeah, so you should get x plus x squared over, yeah, so this should be the answer, right? So again, on this interval, right, we don't know what it is outside. In fact, we at 1 it's infinite, right? It blows up. Okay, any questions so far? Okay, so I'm gonna let you, from there, 26.3b, you just plug in the values, right? Like the first one is just plug in x equals a half. The second one is plug in x equals 1/3. Okay, so, I forgot to write something. Okay, so for 26.4, it says, whoa, 26.4, it says, note e to the negative x squared is this. So how do we get this? So I forgot to tell you from the top, all 3 of these have r equals infinity. So it converges everywhere. And you should expect this, right? I mean, you could plug in any value to e to the x, and there's no problem, right? Like e to some negative number is still very defined, and cosine can take in any value without any issues, right? But like, something like here, like 1 over 1 minus x, you can't take in the value 1, right? But clearly e to the x, cosine and sine, you could plug in x for anything, right? So we have the radius of convergence is infinity, right? So if we had e to the x was this, well, what am I doing? So e to the x was just x to the k over k factorial, right? And so if you replace x with negative x squared, you're sort of replacing, it's just this, right? You're replacing x with negative x squared. And you could check that you get, if you FOIL this, it's negative 1 to the k and x to the 2k, right? You get exactly the thing. Sorry, there should be a factorial here. Okay, so that's not hard. But note the reason you could plug in negative x squared is because, and there's no specification, right? So what the problem is saying is if it will hold for any x in R. And the reason is e to the x convergent, the radius of convergence is infinite. So we don't really, we can make any substitution we want, right? So, okay. So part B, what is right? I'll just write the question, right? Power series for integral 0 to x e to the negative t squared dt. Let me just warn you all, don't try to integrate, I don't know, like 0 to some number, or I don't know, like 0 to some number, like e to the negative t squared dt. Yeah, it's pretty much impossible with single variable calculus. You will need multivariable. So, but you know, so I'm saying we don't know the value. It turns out the value is like pi or something, but so like root pi. I forgot. But anyhow, we just want the power series. So integral 0 to x. E to the negative t squared dt. Well, what is the power series for e to the negative t squared? I wrote it above, right? It's integral 0 to x. Negative 1 to the k, x to the 2k over k factorial dt. Or sorry, it's a t, not an x, because it's e to t negative t squared. Okay, so again, inside your inside your interval of convergence, you can swap, right? But e, the exponential, has radius infinity, so we can always swap. So in this case, we get this. And we all know how to integrate t to the 2k, right? So if you like, the other ones are constant, right? So you're just integrating this, right? So again, k is a constant here, right? Because it's dt, like t is your variable. So anything else is just a constant. And here, if you integrate, you get what? You get negative 1 to the k over k factorial t to the 2k plus 1 over 2k plus 1, evaluated at x and 0, right? So this is math 2b. And similarly, I don't care about 0 because I get 0, so you just get this, right? X to the 2k plus 1 over 2k plus 1. Yeah. Okay. Any questions so far? Okay. So I will sort of skip 26.5 for now. So again, like your homework is like 26.6. So except so this is sine and cosine. I think instead of sine and cosine, your professor gave like sinh and cosh. Yeah, okay. So let's continue on. So let's start with 26.7. What do you all think? If f of x is absolute value of x, is there a power series sum a n x to the n such that f of x is, so basically, can I write absolute value of x as a power series? Is there a power series sum a n x to the n such that f of x is so this one's pretty important. So basically, can I write it as a series with radius of convergence infinity, right? So the thing is, let's assume we can. So f of x is this. But since radius of convergence is infinite, I could take derivative and move it inside, right? I skipped a step, but hopefully we're all clear. It's ddx on the outside, and I bring it to the inside. So here again, it's this, right? N x to the n minus 1. Sorry, I need a 1 here. Yeah, so if you're not really sure about the n equals 1 part, I mean, in this case, I mean, you could plug it in, right? If you plug in n equals 0, you get a x to the negative 1 power, right? That's not really possible, right? If you have a polynomial and you take derivative, you're not going to get a 1 over x as a result. So that's sort of a reality check, I guess. But here in this case, certainly f prime at 0 makes sense, right? F prime of 0 is 0. Right? If you have power series, the derivative at 0, I mean, if you plug in x equals 0, you're adding 0, an infinite sum of zeros, and that's 0. But what do you all know about about absolute value of x? Is it differentiable at 0? So, anyone? No, right? I mean, I'm not gonna go over the proof, but absolute value of x can be written like this, right? Right. So when you're at the left of 0, you're the function x, and when you're to the right of 0, you're the function negative x, right? And at 0, well, it doesn't matter. So if I go to 0, remember what is derivative? It's the slope, right? But like, what's derivative of x? It's 1. But if I approach 0 from the other side, I get negative 1, right? So you see like derivative is not defined, because on one hand I have a slope 1, and on the other hand I have slope negative 1. So yes, but is not differentiable at 0. It's certainly differentiable everywhere else. Differentiable at 0, because x is differentiable and negative x is differentiable. Okay, yeah. So the answer is no. Okay. So let me show you one more cool thing, I guess. So 26.8. I don't know what that 1 is, but okay. So I need to write 1 over 1 plus x squared, right? So 1 over 1 plus x squared. So recall our formula is of this. It looks something similar to this, right? So how can I write 1 over 1 plus x squared as a power series? Well, sorry. So I need a minus something, right? I need something like 1 over 1 minus. Well, how do I get a minus? Well, I do this. This is 1 over 1 minus negative x squared. Yeah? And then this is now the series. Again, this is for if you like, this is, let me write like this. Another way to write this is, right, so i.e. x in, right, if another way to write negative 1, 1 is absolute value of x is less than 1. So here it's absolute value of negative x squared is less than 1, which is still, if you check, it's still the interval negative 1 to 1. So here I get negative x squared to the n. Okay, and here this is just, if you bring it out, make it look nice. It's this, right? Okay, so that's part A, right? Now part B, find power series for arc10. If you like, tan inverse, right? Let me just write, i.e. arc10, tan inverse. So This is nice. So this is why this derivative and integral thing's really nice. It allows you to just, you know, find power series for functions you don't know just by taking derivative, right? So we know derivative of arctan is the thing above, right? It's 1 over 1 plus x squared. So how do and I know this thing, we just calculated it, was this, right? Okay, so how can I get power series for arctan? I have the power series for derivative of arctan. So integrate both sides, right? So again, it should be dx, right? But so here I get arctan is equal to n equals 0 to infinity. So here I'm going to get negative 1 to the n x to the 2n plus 1 over 2n plus 1, right? So again, this is on negative 1 to 1, right? But what you're going to notice is, you know, what about, you might ask yourself, what about like at 1, right? So at 1, it converges, and, you know, so here, I guess what I want to say is we're going to use Abel theorem, right? It's going to, if it converges at 1, it's going to converge to whatever we have. And you could check at x equals 1, x equals negative 1. This series converges, right? I'm not going to do this, but it's just alternating series test, right? I don't think it's that hard. So, but this gives you a very nice way of, you know, expressing pi. So what is tan inverse of 1? I sort of said it, but basically tan of what angle gives 1, right? We're doing inverse, right? So that's how you should ask it. So tan of pi gives 1, right? So tan inverse of 1 is pi. But tan inverse of 1 is also, I plug in 1 to the series, right? 1 to the 2n plus 1 over 2n plus 1. So you actually have a nice formula for pi. Pi is just this infinite series. Yeah. Yeah, so today it's just a lot of calculations. But let's do one more. So I think I sort of skipped 26.5. So again, we all know derivative of e to the x is e to the x, right? So basically they want you to check it the power series way. So if we have f of x is this thing, right? So x to the n over n factorial. Check that when you take derivative, right? It's still the same thing. So let's do it. So here, again, I could just bring it inside because radius of I don't need to write what the radius is because it's true for everything, right? Because radius of convergence is infinity. And this is what? This is, there's a constant term, right? N equals 0. So it's going to go to 1, and n x to the n minus 1 over n factorial. Now, n, how does n and n factorial cancel? Well, n factorial is this, right? Which is n times n minus 1 factorial. So this should just be, yeah. Okay, so, but now I can re-index, right? This I can always re-index the series to start at 0, right? So to do that, what did I do? I subtracted 1 from n, right? So I need to add 1 back. So this is, you know, I replace n with, you know, n plus 1. And you'll see you get the same series. right? So again, just reality check. If I plug in 1 here, plug in first term, right? Plug in 1, I get x to the 0 over 0 factorial. If I plug in the first term here, which is 0, I get x to the 0 over 0 factorial. So that should convince you, like, at least, the first terms match, right? So these series are actually like the same, reality check. Okay, that's all I have for today. So I'll save the last 10 minutes for like homework questions because I know homework's due. But any questions on the notes at least? So again, can anyone tell me if the YouTube channel works? Anyone? Okay, the YouTube channel does work. Okay, yeah. So I'll start posting it on YouTube because cloud storage is getting really, really bad. Okay, cool. Thanks.